Okay, and then so then when we saw that, when we use this, our AX function that we worked so hard to build, and we graphed that, we saw that it graphed like this for a delta x of 0.5. So what I want to do now is I want to pick a point over here. Time is 1.3 seconds. And when time is 1.3 seconds, there's some output so I'm just going to point at it here. So right there, 1.3 seconds, there's some corresponding, where I've got the arrow, that's at 1.3, there's some corresponding output of the A function. Okay? And so what I want to do is, I want to investigate more closely, how is it that the A function calculates that output of A of x? So we're focused on A of 1.3, okay? So our focus is A of 1.3. How exactly is let's just do it right here. So this is the point 1.3 comma A of 1.3. How exactly does that A function calculate that output or y value, whatever it is, right? How does it do it? Specifically, how does it do it? So I have a handout. If you think you can kind of piece it all together yourself, then that's just question number one, which is the question I just asked you. Specifically, how does the rule for AX calculate this value, A of 1.3? How does it do it? I'll get down to all the nuts and bolts of it, okay? If you can't make much progress, then I've done more a structured approach in 2 through 7. So see what you can do just cold, and then if you're really stuck, then you can use the kind of guided practice in 2 through 7. But try just to answer one without looking down, okay? When we get to the ends, pass up and down. I didn't count. So when we get to the ends, pass up and down. Is there any extra on this side? Anybody need markers? So first start by answering, there's a preliminary question there above number 1. What's the meaning? Okay, so what's the meaning of A of 1.3? Specifically, what does that expression mean? And then once we have the meaning, then how does that rule, this very seemingly complicated rule that we've been working on, how does it calculate that value of A of 1.3? Step by step, all the nuts and bolts. See if you can figure that out. You can work together, okay? You can work together. Anybody else need one? Hold on a sec here. Okay, let's start with just the meaning of A of 1.3. The meaning of, so in the context, right? In the context, what is the meaning of A of 1.3? Penny?
seconds, the sand weighs 8.8.
She says at 1.3 seconds, the sand weighs this much. Is that right? Yeah, so it's the total accumulated weight at that moment in time, that current x value, that current time value of 1.3 seconds, right? It's the total accumulated weight up to that point. Okay, so how does it do it? How does this long formula calculate that? So looking down below, so what does it mean in this context, j equals 1? So we come over here and we say, oh, this is going to sum up a bunch of things, right? And what's the first thing it's going to sum up? It's when j equals 1. So what does it mean when j equals 1? McLean? The first interval. Okay? So should I look over here on the right or should I look over here at the left? Yeah, okay, so if j equals 1, then let's work it out here. When j equals 1, what are we talking about? R of what? The rate of the first interval. The rate at the left endpoint of the first interval. What do you think? Which is it? Well, plug it in. If you put j equals 1 in here, what do you get? We're going to go no delta x's over to the right, and we're left with a. This is when j equals 1, you get r of a. And that's the left-hand side of the first, that's the rate at the left-hand side of the first interval. Or in other words, r of 0. What's delta x? 0.5. So we want to start with r of 0 times 0.5. So I got up here, we're going to put in r of 0. R of 0 is 0.216. 0.216. Okay? Should probably do it here. So this is for j equals 1. We're taking, so r of 0 is 0.216. Delta x is 0.5. And so what's the contribution? When j equals 1, what's the contribution to this right here? A of 1.3. How much? How'd you get that? Yeah, it's going to be r of a times delta x, right? So this is r of a times delta x. So we've got, I didn't leave myself room over here. Okay, so we'll do j, first column j, and then we'll do r of something, and then r of something times delta x. So when j equals 1, we actually are just doing r of a, right? Which is this value of the rate, which is taken at the left side of that first interval. And so that's r of 0. And what did I say it was? No, r of 0. 0.2. Okay, and so then r of 0 times delta x is 0.108. So j equals 1 represents this first full interval. And how much accumulation do we get? 0.108 pounds of sand are added on in the first half second. Do you see? And that's what that does right there. Okay, so then we go to j equals 2. What does this mean when j equals 2? So what's going on here when j equals 2? Scott? Okay, can you be more specific? So what? Okay, so then what does this do with that? What does this do with that second interval from 0.5 to 1? Tell me about the calculation that this thing performs. Yeah.
It's the rate at the left endpoint of the second interval.
How does it do that? So how does it get that?
It takes the rate at the first interval and adds it.
So it takes the rate here and it adds to this rate. Is that what it does?
It takes the quantity and adds it.
Takes the quantity and adds it. What are we saying? J equals 2. So plug it in. J equals 2. What do you get when you plug J equals 2 in here? A plus 1 delta x. And so we get A, and A is 0, and 1 delta x is 0.5. So we're going to take R of, sorry, that shouldn't be that. This is generic, right? So this is going to be now R of 0.5. You see that how it does that? You put J equals 2 in there, and it says, okay, now the input into R is going to be A 0 plus 1 delta x. 0 plus 1 delta x. That's going to give me that rate right there. And so for the whole second interval, we're going to apply that rate, which is R of 0.5. And what is that? 2.28. 2.28. Okay, so this is 2.28, and therefore, times delta x is 1.14. Okay, what about J equals 3? J equals 3, what do you think? What's that? He doesn't want to do it. Do we do J equals 3 or not? So I'm doing A of 1.3. Aren't I in the third interval? I'm in the third interval, so don't I want J equals 3? What's that? Right, so this is the place now where we get to this partial interval, right, for the current value of x. So what about my j's? Done? We're done with the j's, right? We're done with the j's because, remember, this adds up all the accumulation from the full intervals, and we had 2 full intervals, right? There and there. And now this second term does what? Partial interval. So we want R of left of x. What's R of left of x? R of 1. And we want x minus left x. What's that? What's x? 1.3 minus left x. And so that value right there gives us 0.3, or how far we're going in that partial interval. So we've got R of 1, and over here that's going to be R of 1 times, not times 0.5, but R of 1 times 0.3. Okay, so R of 1, I believe, is 5. Let's see. Oh, no. Okay, this is what I wanted up here. R of 1, 5. Okay, so R of 1 is 5, so therefore the little bit of accumulation we get from the partial interval is how much? So R of 1 times 0.5? No, R of 1 times 0.3. So how much do we get? 1.5. Okay, so from the first full interval we get that much. R times delta x, and we saw how that worked. When you plug in J equals 1, you get R of 0 times delta x. When you plug J equals 2 in, you get R of A plus 1 delta x, or R of 0.5, and we get 1.14. And then the partial interval, R of 1 times that little part of delta x, or 0.3, we get 1.5. So how are we going to get A of 1.3? What's A of 1.3? Ratio. Okay, anyone do it yet? 2.748. Did I do that right? Okay, let's check it. So let's see if that's what it did. So I'm going to come on here and put it at 3. Look at that. I know you can read that, but right there it says x is 1.3, 2.748. Nailed it. Okay, so you see how this is doing what we've been working on this whole time, adding up k delta x plus k delta, or r delta x plus r delta x plus r delta x, and then so the left-hand side gets all the full intervals, and the right-hand side gets that last partial interval. Doesn't make sense. So it works. And what's especially cool is, remember when we first started doing piecewise linear functions, we had to do them a line at a time, right? We had to do the first line and the second line. We had to actually do it in pieces. So the power of this summation notation and then being able to have that floor function means we can write that piecewise linear function as one line. It's a really powerful thing. We can write it in one line, and it knows to do this, right? It knows to go linear and then chunk and then linear like that. Not in many lines, but in one line. Anybody have a question? Okay, so here is the beauty of graphing calculator. So is this a nice, accurate accumulation of the weight of sand function? And you've been asked many times, how do we make it better? So how we want an accurate accumulation function. Smaller intervals, right? Because what happens when you make smaller intervals? What happens to the step function? It does a better job pretending to be the original rate function, right? It does a better job. So let me turn off this one for now. So if I were to, this is what the beauty of graphing calculator. We can put in this generic step function and this generic a function, and I can just make delta x a slider. And all I have to do is, here's delta x of, say, let's do 0.1. Wow, long time coming. Okay, so here's about 0.1. So, do you want to build that accumulation function by hand? Want to do that? So we'd have to build a piece for each one of these little chunks, right? But we've already done the work, right? This is going to do it for us. That's going to do all the work for us because it's in terms of delta x. Okay, and I can make even delta x even smaller. It's 0.015. So now I'm going to turn off the original rate graph. Turn off the original rate graph. What do you see? How is it doing at pretending to, this is a step function, right? These are constant rates. How is it doing at pretending to be the original function? Pretty dang good. If you're in the back row, you probably can't tell the difference, right? You can't tell the difference. Okay, so I think I can, no, that's that. There it is. There we go. So there's 0.005 delta x. Now everyone just always sees the rate function. But this is a piecewise constant rate function. So now if I turn on the a function, how about that as an accumulation function? What did I have it? Purple? Is it a curve? Oh, I saw some this and I saw some this. Is it a curve or not? No, okay. But for our purposes, it's close enough, right? It's almost indistinguishable from what we're seeing. This is almost indistinguishable from the real rate. So I can back up here and make delta x larger again. And so as delta x gets smaller, we see that curve on the right, our accumulation function, it's converging, right? It's converging on a nice smooth curve. And so when we get small enough, then it's small enough, and it's virtually, for our purposes, it's the same as the actual true accumulation function. Okay? So it's kind of like we made it, we did it, right? So after a month, we've worked to get what is the given a changing rate function, what's the true accumulation function? Okay? And so this is what graphing calculator can do for us. Okay? Hope you appreciate this. It's really cool stuff. Okay, so we're going from here. We are going to this. Is there a question? Okay, so this is what we call fine-tuned accumulation. Okay, here's our accumulation function. That gives us the piecewise linear accumulation. And so we say when delta x is sufficiently small, when it's small enough, like the distance between parts of a cell, okay, or distance between electrons in an atom, Okay, when it just gets sufficiently small. Now delta x, we call this dx. dx. So that's the same thing as delta x, but when delta x is small enough, really small, so that our, small enough, okay, small enough. And so then our function becomes this. So everywhere we had a delta x, now it's dx. So this is like that last curve I showed you when delta x was 0.005. Okay, so this version, when we have dx, a very, very small delta x, it's indistinguishable from the precise accumulation function associated with the rate. Okay, so again, this is indistinguishable from the precise accumulation function that we've been after all along. So for that we have a simplified notation. Okay, so this is the simplified notation of our ax function when delta x is very, very small, or dx. So these two are the same. This is just a lot more compact and easy to read. Okay? It's a lot more compact and easy to read. So, based on everything we've learned about building this accumulation function, let's see why this notation is what it is. So, do you recognize things in there? Can we associate it with our idea of this accumulation function? So, what do you see there that ties into what we've learned? Ruby, can you just tell me one thing that you see there in this that relates to this accumulation function that we built?
The R.
R? So our rate function, right there, right. That's our changing rate of change function. It doesn't have to be changing, but most generically it is changing rate function. It's the same R that we were using to build our step function, right? It's the same R that we built the step function from to calculate the little bits of accumulation. Something else? Yeah.
With the sigma and the Germans.
Oh, yes. She knows. It's a German S. It looks like an S, right?
Yeah. The parameter set on it are the same. So instead of, or on the top, so like x.
Well, let's just talk about the German S. What does the German S represent here? What might it be talking about that we're... Yeah, sigma, or the sum. That's right. So it's just another way, instead of sigma, it's again, right? We're summing up. And what is it we're summing up? Do you see what we're summing up in this notation? Is it apparent? Moises? Okay, and how do you see the accumulation here? How do you see it? Where do you see it? Does it show up? Yeah.
Is it the A starting point and the X? The distance between A and X?
Okay, so you're talking about something else. So you're saying you see that A here. What did A represent?
So like the accumulation from there to there.
Okay, so this is where the starting point of the accumulation is still A, right? Starting point of accumulation still is A, and we're going to accumulate up to what? X, which is the input, right? So this is a function. So it's a function of, just like this was, a function of where we accumulate to, right? So X is where we accumulate to. Or the end point. Okay, so back to the question, where do we see accumulation in this? So we got the German S, we got the sum. Where do we see the actual accumulation? Where does it show up? Change in T, that's the accumulation, is that right? Is that our accumulation? Okay, so that's the interval, dt. And so what makes up the accumulation? Tell me your name again, sir? Yeah. Harrison, where do we see the accumulation in this?
With the German S.
Well, that just means sum. But what are we summing? We're summing up.
To the x value.
Okay. But again, where do we actually see the accumulation? D of t. Is the D of t our accumulation?
So the RT times the D of t is our y value.
Right.
Just summing each one of those up.
Not y, but
Change.
delta y, right? What are we summing up? Change in y plus change in y plus change in y plus change. And how do we calculate those changes in y? We've been doing it r times delta x, r times delta x. So do you see it? So now our delta x is like dx. I'm going to do this in red so it stands out. But this whole thing is like k delta x. That's our delta y, or because it's really small, it's dy. So now delta y then would become dy. A little itty bitty bit of accumulation. And we're going to sum all those little bits of accumulation up, starting at a and ending at x. And then as we let x grow, we're going to get a function. So it's all it's all there. Okay, so it's everything that we talked about. It's the sum from a to x. So we say this German s sum is called the integral. Okay, the integral. So it's the integral from a to x, or the accumulation starting at a up to x of a quantity whose rate is r of t. So it's accumulation of a quantity whose rate is r of t. So it's all packed in the small notation. So then the question is, what happened to the full intervals and the partial interval? What happened to the full intervals versus the partial interval? What happened?
They're so insignificant.
What do you mean?
Like, well, the delta of x is so small now.
Right?
I guess it doesn't even matter.
Right, yeah, Jackson.
The difference between a full interval and a non-full interval is so insignificant that it's basically.
Yeah, I mean when you make things really, really small, then it just basically it's all just super small intervals. It's just super small intervals, all of them. So the fact that you would have a partial is trivial. It's like they're just all microscopically small. Okay? And so all we have to do is think about the sum of all the itty bitty bits. Yeah.
I know this is you just said sufficiently small, but like at what point is sufficient?
Yeah, so that there's no number, right? There's no number. It's an idea. It's an idea that when delta x is like microscopic or atomic, then it's close enough that we can't tell the difference. And it's indistinguishable from the actual curve. Okay, so there's another question that some of you might be asking here. So we introduced a new variable, t. What is t about? What's that about, t? I mean, we were doing r of x delta x, or r of x delta x, r of x delta x. So why do we have t in there? Yeah.
Does that signify a changing x?
Does it signify a changing x? What does x mean in this situation? Okay, and what does the input mean in this function? What's that? Where we accumulate to, right? Where we the stopping point of the accumulation. Okay, so what'd you say? Say it again, Adam.
Changing x
From where to where?
from our a to x.
Yeah, so don't we need to have x means the end, right? It's the last x value that we're accumulating to. But this sum of all these little bits is saying we're going to sum up all the bits as we start at a and go to x. So t is an x value, but we need a different parameter to signify that changing x from a to x, because x itself is where we accumulate to. So it's not time necessarily, because you don't have to. So it could have been u, like for instance, so this could be u. That would be perfectly fine too. So ru du. And now u is an x value, signifies starting at a and marching up to x, which is our final place that we accumulate to. So would it work to do, say, a to x, rx dx? Would that work? Is that okay too? Yes or no? Is that a hand? Yeah, in the blue, I'm sorry. You'd say no. Why not? Distinguish one from the other. What would what would this do? What would this do different from this? So can you maybe talk about that? I'm going to set up, we'll do a little demonstration on GC. But what will this do differently and not what we want from this? Okay? Talk about it. So what will that do? Okay, so in order to do this, what I'm first going to do is I'm going to set up a function. The actual so graphing calculator we can graph these accumulation functions as integrals. So I'm going to call it TA for true accumulation. Okay, so TA is so a of x is our approximate accumulation function, right? And so now TA is going to be like some true accumulation. And so what you do is, I think, Command Shift I. No, Control Shift I. Good. Okay. Control Shift I brings up the integral symbol. Okay, which has the same meaning, same mathematical meaning that we just talked about. So we want it. In this case, a was 0, and so I'll make that a function. I'll make that a function of x. So where do we want to accumulate to? X. And what is our? I called it r, and so let's go with u, like I said. So we'll do ru du. Oh, and we got to graph that. So y graph that over on the right equals TA x, and we won't graph it. We'll graph it black. Okay, so here is our delta x of 0.5. So I'm graphing our a function with delta x 0.5, and I'm graphing the integral function, which represents the true accumulation function. And so what will happen when I increase or decrease delta x? What's going to happen? Our step function will approach. This is cool. We're not doing this in the other calc classes. Okay, so notice how that the pink one is the approximate, and it's converging on the true as the step function does a better and better job reproducing the rate. So here's that 0.005. Where are you? So there's 0.005, and this is kind of the idea of dx, right? dx, where our step function reproduces the original rate function, and the accumulation function then is virtually the same as the true integral accumulation function. Okay, so now we were asking this question, what would happen if we did r of x instead of, there it is, instead of r of u du, what would happen if I did r of x dx? R of x dx. Yeah?
Would it just go straight to that point? It wouldn't give any changes.
Okay.
Just to that one point.
So let's pick an x value. So let's pick x equals, say, 1.5. I'm going to pick x equals 1.5. So then what's TA of 1.5? What would the rule be? From 0 to what? 1.5 of r of 1.5 now. So this is not this. This is if we did r of x dx. Then it'd be r of 1.5 dx. And what would that do?
It would use the rate at 1.5 for the entire interval.
Good, excellent. So what you're going to do is you're going to accumulate from 0 to 1.5, but you're going to accumulate not the rate function, but this constant rate. Do you see? The rate at the end. So you've got this rate at the end here, 1.5. What's it going to do from 0 to 1.5? It's not going to accumulate based on this rate curve, but based on this straight line. Okay, so let's and that's not what we want. If we want to accumulate from 0 to 0.5, we don't want it using this rate function, which is the rate at 1.5. We want it to use this rate function to do it. Okay, any questions on that?
Is that like a common mistake that people make?
Yes, they will forget to use a different parameter there. If it's the function, right? If it's the function and you want that input to be where you stop accumulating to, you need a different parameter there. Representing an x value, but representing all the x values from 0 to x. Okay, so on the back side of your handout, make sure I got it. There are 6 integrals, right? Integrals. So for each, we're going to determine if it represents a valid accumulation function. Does it represent a valid accumulation function for the rate of change function that's implied by the expression? Okay? So, and then we're going to identify all the parts of the expression and describe the meaning of what the whole thing represents. Okay? So it's a combination of saying, is this a valid accumulation function like this one we just did, 0 to x ru du, or is it something else? And then what do all the pieces mean? So we're just reviewing, what do all the pieces mean? Okay, so definitely you want to have a partner, you want to be talking these things out. So talk this thing out. Okay, go. But also why the reason why. And the problem that we just talked about, you'll just basically, you're just going to be calculating accumulation for constant rates all the whole way. That's right. So if those were all T's, they're all here. So it's over here. Okay, but X is just as a factorial as you then you have this situation. You don't get 0 to 8. Yes. Is it okay?
Yeah, that would not actually make sense. Because you're going to have
I think that.
Like if you were playing
That was definitely.
so
right, so you're simplifying. So if these were used, 0 to 8 are all outs. So I'll see. So X just becomes another placeholder. Like you. It's just a placeholder. Yeah.
Yeah, it's just to be honest.
like the first one, summation
Placeholders. Right, just like we talked about, like so you could have Rx, RT dt or RU dt. So this V is just using V. Yeah, that's all. Yeah, so because we're you're sliding. You're trying to make those and you don't get it. Okay. Oh shoot! All right, so we got to go. So I lost track. So this is good. This is good. We're accumulating. It's a function accumulating from 4 to x. And what's the rate of change of this? What's the rate of change function? Little f. Little f is our rate of change function. This one doesn't work. Okay. This one doesn't work because you can't. These can't match. If these match, then you're not going to be accumulating at a changing rate, right? You're going to have every time you put an x in, it's going to be just a constant rate the whole way. Okay, doesn't work. How about this next one? Accumulating from a to x for this right here. It works. What's the rate function? This whole thing is our rate of change. Okay? How about this? From 0 to 8, cosine x cubed plus x cubed dx. It's okay. Why? Because this is an 8. X is, in this case, x is just like u or v or t or anything else you want, because this is an 8. This is perfectly fine. It's the accumulation from 0 to 8 of the quantity changing at this rate. Did you hear that? It's the accumulation from 0 to 8. So, is this a function or a number? No, it's a value. It's the accumulation starting at 0 and ending at 8 of the quantity that has this rate function. You will get a number for this. Right? It's how much when you start at 0 and end at 8 for a quantity accumulating at this rate. It's how much accumulation you'll have when you stop at 8 starting at 0. This is a number. It's not a function. This is a number. Does that make sense? That's really important. How about this next one? Does it work? Number or function?
Number.
This is a value. This is a number. This is not a function. Okay? Work? Doesn't work. Doesn't work as, what we're trying to do. Okay, have a great weekend.